Okay, thanks, Katie and Corolla. What I'm going to be talking about is similar to what Melanie's going to be talking about for the Arizona site, but this is sort of taking this version of the logic tree that Katie just presented and doing some sensitivity analyses on those certain branches and features of the logic tree. So this is going to be for Diablo specific. If I want to step back first, I want to say, okay, you know, what goes into the hazard will be not only the ground motion part, but like Norm said, there's a whole group and studies going on to develop the source model. And so if we go back and we look at sort of what I presented at the first workshop in terms of what are the significant sources to Diablo Canyon, this shows a plot of two sets of hazard curves. On the left, we've got the PGA hazard curves. On the right, we have half a hertz or 2 seconds. Let me just point out that the x-axis is a normalized ground motion value because we're not concerned specifically about absolute ground motion values, say at the 10 to the minus 4 level, but we're concerned about the relative contribution for all the sources. So this is showing in both cases the contribution from individual fault sources, which are listed down here in the legend. And the thing that jumps out, especially for PGA, is you've got a cluster of sources which are contributing basically most of the hazard at the site. And these are the 4 sources that have been sort of talked about and people may be familiar with or not. It's the Hosgreave fault offshore. It's the shoreline fault, which comes within less than a kilometer of the site. And then you've got 2 reverse faults. One, the Los Osos fault, and then the San Luis Bay fault. And those are both dipping under the plant such that the plant is sitting on a hanging wall. So when you look at those 4 sources together, those are sort of the significant contributors. And so for my sensitivity analyses, what I'm doing is I'm basically running those 4 sources and doing that with the different variations of the ground motion models to see how that impacts the hazard at the end. If we look quickly at the same type of thing, but look at a deaggregation plot, we can see that at 10 to the minus 4 for the probability level, we've again got PGA on the left and half a hertz or 2 seconds on the right. You can see all the hazard or most of the hazard is coming from these sources, the 4 sources I mentioned that are very close to the site. And so this sort of reiterates the fact that, okay, if we want to do sensitivity rather than running the full global or regional source model, let's look at the sources that are contributing most of the hazard to the site and sort of isolate those and then do the sensitivity on the ground motion aspects. So going sort of along what Katie had mentioned, we have to first define a base case. And for our base case, we've got the 5 2008 NGA West 1 models. And so you can see them listed here. They're equally weighted, and as Katie mentioned, we have this epistemic uncertainty model applied to them depending upon the fault source type, whether you have the large strike slip sources or whether you have the reverse faulting sources. And again, we've done everything for a VS30 of 760 meters per second for these sensitivity plots. These are the additional models that we're now considering, and some, you know, we've been over this before, but again, the first 5 are the new versions of the NGA West 2 models. And then you have 4 which are non-NGA, if you want to call them that. You've got the GK model 2013, the Zhao et al. 2006, and as I said before, it's based on the site condition is based on a binning of VS30 values. So this is for SC1, which is greater than 600 meters per second. You have the European, the Akhar et al. 2013, and the Bindi 2011, which is again a site class based on a VS30 of greater than 800 meters per second. Just to show some suites of hazard curves, this is sort of before we sort of boil this all down into tornado plots, but this is just to give an idea of what sort of distribution and range we have. These are the mean hazard curves for PGA, and I've got 2 versions on this slide, and they're very similar to what I had shown before in the first workshop. On the left-hand side, we've got the individual hazard curves by each GMPE, color-coded in line type here in the box, although it's probably difficult to distinguish in the back. And that is using the full median prediction and as well the aleatory sigma model for each of the individual GMPEs. On the right-hand side, what we've done differently now is we've taken the median ground motions from each of the individual models, but assigned a fixed sigma value of 0.65. And so this is basically putting the sigma value the same for all the models running the hazard and showing what is the difference in the median estimates of the ground motion. One of the things you may not be able to see too well, but there is a dash curve which is coming down quite a bit lower than all the other curves here, and that is the Bindi model. And so I mentioned in my first talk this morning, the Bindi model tends to give lower median ground motion values, but because it has a high sigma value, by the time you throw the sigma back in, it's falling within the mean or the distribution of the curves here. And again, these are for normalized ground motion values across the bottom axis. Just to show what the similar type plots are for 1 second, you can see again on the left you have the full median and sigma values of each of the individual models. On the right you've got the median sigma values or fixed sigma value 0.65. If you remember back, this is a wider distribution in hazard curves than we saw for PGA. It's something that we're seeing when we're running these models. And as well, the Bindi model actually at 1 second or 1 hertz is actually with the fixed sigma of 0.65 is coming into the distribution. So the median values for 1 second or 1 hertz from Bindi are not as low relative to the other models. So before I go to the final sets of plots, which are the tornado plots, which have been developed and we present them in our working meetings to allow us to sort of investigate outlier models and certain aspects of models that we want to do more research on and get a better understanding, and people will be talking about tomorrow and the rest of this workshop, is how do we calculate the tornado plots? So given if I were to run a base case hazard curve, being this red line here, and I ran 2 additional cases, so I'm calling it a GMPE high and a GMPE low. And so I want to take a certain probability level, so let's say 10 to the minus 4, and I come across on my base case and I read down and I get a certain ground motion value, a little bit over 2, between 2 and 3 G. Again, on a normalized PGA, it doesn't matter in this schematic diagram as to what whether it's normalized or not. So that gives me my base case ground motion level. Then I do at the same probability level, 10 to the minus 4, read down and calculate the ground motion for the high and the low, the green and the blue values. I then compute the ratio of those ground motion values, and that gives me my tornado plot point. And so what we do and what we'll show is we break apart the logic tree into certain branches, and we plot the distribution of those ratio data points for each of the different branches of the logic tree, so we can try and understand and get a better understanding of what aspects of the models are important and which ones may not be as significant to the overall hazard at the site. So this is a sort of a word plot of sort of the 8 cases that I will be showing and Melanie will be showing for these tornado diagrams. And so let me go through these and explain them as to what we're actually tweaking and modifying. So the first one is the sigma. And so what we've done is, again, we have a base case set of 5 NGA West 1 ground motion models. And we take those median predictions of the ground motions from those 5 base case models. But on top of that, rather than use their median or their sigma models, we apply the individual sigma models from each of the GMPEs. So as an example, if we're looking at a hazard run where we'd run the median ground motions from the 5 NGA models with the sigma model from the ASK 2013 model. And then we do the same thing with the BSAA sigma model. And so what we're tweaking and what we're changing out is within the hazard interval, we're running the median ground motion values, but we're swapping in a different sigma model to see how that sigma model impacts things. Related to that is we then do the same thing, but we do it where we modify the phi term. So as Katie had just mentioned, there are 3 options on the phi term. There's a constant term, there's a magnitude dependent term, and there's a magnitude and distance dependent term. And so we do the same procedure where we basically take the median ground motions from the base case, but we swap in the sigma model from a different GMPE with this additional phi SS correction. Because 2 of the models, well, the Idris relationship for the 2008 and as well the new NGA2 model doesn't break their sigma apart, we can't run those cases for this phi SS, and as well the GK model doesn't have their sigma broken out into the phi and the tau terms. The next one is similar to what I had just shown before. That's running the individual GMPs with their median predictions and as well their sigma models. Then we follow that up. I'm calling it the GMP median. What that means, it's a little bit confusing, I guess, is that we're looking at the median aspects of the model. So we're fixing the sigma. So the sigmas for all those cases are fixed at 0.65. And then we get into a set of 4 cases, and this might need a little bit of explaining based on the words I put up there, which is limited. For Diablo Canyon, we've got two main source types. We've got the 2 strike-slip sources, the Hosgri and the Shoreline, which are strike-slip sources close to the site, and we have 2 reverse sites, or 2 reverse sources, the Los Osos and the San Luis Bay source. What we want to look at is we want to look at, well, how different are the results based on sort of the GMPs and their prediction of strike-slip ground motion as opposed to, say, reverse hanging wall ground motion sites. And so what we do here is for this, quote, strike-slip case, is we take the base case hazard curves from the 2 sources that are reverse sources. So for the San Luis Bay and for the Los Osos fault, we calculate the base case hazard contributions of the hazard sources from those two sources. Then for the two strike slip cases, what we do is we calculate the hazard curves based upon using the individual GMPEs. And so we add those together to get the total hazard curve. So we've got a total hazard curve that's coming from the ground motion, or the hazard curves from the reverse being the base case, and the strike slip being the individual GMPEs. We also do the same thing, but in a similar sense as we've done up above for the other cases, is we do that, but we fix the sigma at 0.65. Then if we swap that, we say, okay, let's take the base case hazard curves from their two reverse sources and use that as sort of a base case for those two sources. But for the strike slip, we take the individual GMPEs and we add those together. And so we come up with a combination of basically 4 cases, because we have a pair where we take the median and the sigma, and as well we take the median and the fixed sigma. Melanie will show for the Arizona site, she'll have the strike slip cases, but her cases are not reverse or normal faulting. So when we do that, this is what it boils down to. This is a tornado diagram. So I'm showing you PGA at 10 to the minus 4, and this is the ground motion ratio on a log scale from 0.1 up to 5, so it doesn't quite go 2 decades, but they're log scales. And I've got the 8 classifications in the same order that I had shown before. On the previous slide, we've got the sigma, sigma phi SS, the GMPEs, GMP median, strike slip, strike median, reverse, reverse median. The individual GMPEs are differentiated by different symbol types. And let me explain why there's such a clustering and a sort of shotgun pattern up here. What we're showing on the first line are the 5 original NGA West 1 models by their symbols. And then on the next line down here, which are these symbols, they're separated vertically to sort of help distinguish, but that's the next set of the 5 NGA West 2 models. And so that's a differentiation. This is basically showing the difference in using the NGA West 1 or the base case models, the individual cases, to the NGA West 2 models. So for this example, you can see that based on the different sigma models between NGA West 1 and NGA West 2, you've got a little bit of an increase in the ground motion values using the new NGA West 2 models. Then the next line down, which is a little bit more spread out here, these are the 4 non-NGA models. So you can see, although I don't know how easy it is, the green open diamond here is the Bindi relationship, and then the solid upper triangle is GK relationship. So these are the 4 non-NGA relationships, and you can see there's a bigger spread, and that makes sense because, as I mentioned before several times, is the Bindi has the highest sigma. And so applying that sigma model from the Bindi model leads to a higher hazard or higher ground motion. And then finally, the last symbol that I'm plotting here, this beach ball, is actually the average of all of these data points. So if you just want to look at the average of each of the branches, you can see it's this symbol, this symbol, this symbol, down all the way for each of the cases. What you can see here is, as I mentioned, there is a spread here for the non-NGA models as compared to the NGA, either 1 or 2 models. And as you can see, as you come down here, the significant things are things like the sigma and as well the GMPEs individually by themselves. This is for PGA at 10 to the minus 4. If we now move to 5 hertz at 10 to the minus 4, you can see now that the Bindi model is actually jumping out quite a bit higher, especially for the sigma case. And so it's a combination of running that median sigma for the Bindi model and as well the high sigma for the Bindi model. You can see it's a similar type of distribution, and these are the types of plots that we've been presenting at the working meetings to help us sort of understand and sort of focus our energy and our research on specific aspects of the models. And this will be something that going forward in this workshop, that certain aspects of the models themselves and the comparisons between the models I'll present tomorrow and will be leading the discussion. This is now for 1 hertz, again at 10 to the minus 4. You can see now what we're getting is we're getting a bigger distribution of the models here. You can see that the Bindi model is still coming in high for these cases. And as well now you see the Zhao model, which tends to have a high median ground motion prediction for the 1 hertz and 2 second case, is starting to pop up as well. To go along with these, and I'll show some tomorrow, is something that we also produce for our working meetings, are plots of deterministic scenarios of, say, controlling earthquakes and events, and I'll go through that tomorrow a little bit in the presentation as well. But that helps us understand sort of the distribution of these data points, and as well provides a sanity check in the sense that we have a comparison of deterministic spectra, both median and sigma, for the suites of models. And we can make sure that these are making sense and try to understand. And then leads us to the next step of looking into the certain features as to how those features of the model were developed. This is for half a hertz at 10 to the minus 4. You can see we're trying to get even a bigger distribution. So again, this is the GMP median. So this is just based on the median predictions. So the sigma for all these data points are fixed at 0.65. And you can see we've got 2 that are on the high side and 1 that's on the low side. This is the ASB, the Akar et al. And then these 2 are the Zhao and the GK relationships. And so from this information, we can break it down and sort of try and understand what's important to the sigma in helping us develop our ground motion model. This is now PGA at 10 to the minus 6. The main difference between this and the first tornado plot I showed is it's a little bit wider distribution in the data points. Individual trends and individual models are still very similar. And then finally, this is 1 hertz at 10 to the minus 6. And so here you're starting to get ground motion ratios up to about 2. And this is, again, the GMPE, just to remind you, is using the individual GMP median and sigma model. So this is the Bindi, and this is where you're starting to see that large sigma starting to have a bigger impact, as you would expect, as you get down to the 10 to the minus 6 level. And then these are just a list of the references of all the models.